Welcome to video 1 for this unit on introducing exponential functions. In this video, we're going to focus on exponential relationships. Relationships with exponential change have a quantity that is repeatedly multiplied by the same amount. The growth factor is the amount that is repeatedly multiplied in the exponential relationship. Here is an example. Suppose a population of cells starts at 500 and triples every day. The number of cells each day can be calculated as follows. We can see that the number of cells, p, is changing exponentially, and that p can be found by multiplying 500 by 3 as many times as the number of days, d, since the 500 cells were observed. The growth factor is 3. To model this situation, we can write this equation. P equals 500 times 3 to the d. Some quantities, like this cell population, increase by the same factor at regular intervals, but sometimes a quantity decreases by the same factor at regular intervals. Let's look at an example. Suppose a bacteria population starts at 100,000 and 1/4 of the population dies each day. The population one day later is 100,000 minus 1/4 times 100,000, which can be written as 100,000 times 3/4. The population after one day is 3/4 of 100,000, or 75,000. The population after 2 days is 3/4 times 75,000. Here are some further values for the bacteria population. In general, d days after the bacteria population was 100,000, the population p is given by the equation p equals 100,000 times 3/4 to the d, with one factor of 3/4 for each day. Situations with quantities that decrease exponentially are described with exponential decay. The multiplier, which is 3/4 in this case, is still called the growth factor, though sometimes people call it the decay factor instead. Here is a graph showing the amount of caffeine in person A's body, measured in milligrams, over a period of time in hours. We are told that the amount of caffeine in the person's body changes exponentially. The graph includes the point 0, 200. This means that there were 200 milligrams of caffeine in the person's body when it was initially measured. The point 1, 160 tells us there were 160 milligrams of caffeine 1 hour later. We can use the graph to find out what fraction of caffeine remains in the body each hour. Notice that 160 divided by 200 equals 4/5, and 128 divided by 160 also equals 4/5. As each hour passes, the amount of caffeine that stays in the body is multiplied by a factor of 4/5. If y is the amount of caffeine in milligrams and t is time in hours, then this situation is modeled by the equation y equals 200 times 4/5 to the t. Graphs are useful for comparing relationships. Here is another graph representing the caffeine for person B in milligrams measured hourly after an initial measurement. The graphs reveal interesting information about the caffeine in each person over time. At the initial measurement, person A has 200 milligrams of caffeine, while person B has only 100 milligrams. The caffeine in person A's body decreases faster. We calculated already that the growth factor is 4/5. The caffeine in person B's body went from 100 to about 90 milligrams, so that growth factor is about 9/10. This means that after each hour, a larger fraction of caffeine stays in person B than in person A. Even though person A started out with twice as much caffeine, because of the growth factor, after 6 hours, person A had less caffeine than person B. An equation representing person B's situation would be y equals 100 times 9/10 to the t. Let's look more closely at person B. We can use the equation to answer questions like this one. What were the caffeine levels before the initial measurement? We could go backwards and calculate the caffeine levels 1 hour ago, 2 hours ago, and so on, or we could use the equation. The caffeine levels are 100 when t equals 0. 2 hours earlier, t equals -2. Then the amount of caffeine, y equals 100 times 9/10 to the -2, or y equals 100 times 10/9 squared. So y equals 123.5. This means that 2 hours before the initial measurement, person B had 123.5 milligrams of caffeine in their system. 6 hours before, t equals -6. Then y equals 100 times 9/10 to the -6, or 188.2. So 6 hours ago, the caffeine level for person B was 188.2 milligrams. Thank you for watching video 1 of 4 for this unit on introducing exponential functions.